Hello, calculus fans. Let's find the point on the sphere x squared plus y squared plus z squared equals 9 that's closest to the point 2, 3, 4. So you got the sphere out in space, there's a point somewhere, and you are at the point and you want to get to the sphere as quickly as possible. Now there's a solution that doesn't require any calculus, but what we'd like to do here is just demonstrate the use of Lagrange multipliers. So the distance from an arbitrary point P with coordinates x, y, z to the point 2, 3, 4 is the square root of x minus 2 squared plus y minus 3 squared plus z minus 4 squared. And we want to minimize this distance. We're going to use the trick that we talked about before. Instead of minimizing d, we'll minimize d squared. That way we don't have to deal with that square root. So that means it's our goal to minimize the function f of x, y, z equals x minus 2 squared plus y minus 3 squared plus z minus 4 squared. That's the radicand, right? We dumped the square root and we just work with this function. And this is all subject to the condition that g of x, y, z, which is equal to x squared plus y squared plus z squared, must equal 9. So the method of Lagrange multipliers tells us to set del f equal to lambda times del g. Del f looks like this. It's a vector, 2 times x minus 2, 2 times y minus 3, 2 times z minus 4. And del g is just 2x, 2y, 2z. That gives us these equations when we set del f equal to lambda times del g. If we solve for x, y, and z, then we get something that looks like this. You should double check the algebra on this. Now we don't actually need to know what lambda is, but what we're going to do is we're going to solve for lambda. Once we do that, we plug them back in here, then we get the values of x, y, and z, the critical points that we're interested in. So we'll plug those values of x, y, z into the constraint equation, and we get this. 2 over 1 minus lambda, quantity squared, plus 3 over 1 minus lambda, quantity squared, plus 4 over 1 minus lambda, quantity squared. That has to equal 9. So that all simplifies to 29 over 1 minus lambda squared equals 9. Let's continue with our algebra. We want to solve for lambda. 1 minus lambda squared is equal to 29 over 9. Then we can get rid of the square by taking a square root. Just have to make sure to introduce a plus or minus. So finally, we come up with an answer for lambda. Lambda is 1 plus or minus square root of 29 over 9. Now if we take lambda equals 1 plus square root of 29 over 9, this is what we get for the values of x, y, and z. If we take lambda equals 1 minus square root of 29 over 9, then we get a different value. Notice that these two are the same except one has all negatives and one has all positive. That means they are antipodal points. Antipodal, A-N-T-I-P-O-D-A-L, antipodal. They are on opposite parts of the sphere. So like the North Pole and the South Pole are antipodal points. Now I hope it's clear geometrically that 2, 3, 4 is closer to this point, so that's actually the answer we're looking for. Now maybe you don't want to have to rely on that kind of geometric intuition. Just plug in both of these points into this distance function. One distance will be smaller than the other, and that's the answer that you want. Okay, that's all for now.